Do they hand out anything? Do you all come in here, or you just sit down? I don't know whether there's flyers. Are there flyers?
I don't know. I think something there.
Okay, good evening, everybody. So, how are you tonight? Good, ready to do some observing? Okay, so we have a very special talk for you today, but you need to be prepared for it. So, how many of you know what laser craze is? Nobody? Yes. Ah, there is somebody, laser craze. Have you been there? There we go. It's a laser tag game place. So it's like going around with laser guns and laser craze. So more than 20 years ago, when I first met our distinguished speaker tonight, Ronald.
Say the name.
I thought I was in laser craze land. And ever since then, I've actually loved going to his lab. Actually, labs. He has labs in any building in this campus. He invents new things all the time, and there is a new lab pops up. But it was like laser craze. You would know because there were different color laser beams, like green and red, and one going this way, another going that way, and blue sometimes. And I just loved it. And then it was just fun, but I started learning what he actually does, and it was amazing. And turned out that we could even figure out to do a lot of things together. But Ron had been educated down in Duke in the 80s, and then came to Harvard to get his PhD, which he got just around in 91 when I was coming here, and then soon afterwards I met him in his laser craze lab. And his expertise from the very beginning was in all of those really new ways to study matter or the human body or the universe, as you will see today, the interior of stars, the interior of planets, discovering planets. And he comes up with a new idea every couple of years. So I can't wait to hear what his new invention will be next year. But in the meantime, he's made such a long list of inventions and interesting gadgets, from new ways to do MRI imaging to new ways to discover planets around other stars, that I will have to take his whole time to even just give you the list. The more important thing is that here you have a colleague at Harvard who has really enriched the university, but also, I would think, the world with his inventions. And not surprisingly, he's a founding member of most of the interdisciplinary initiatives, like this one, the Origin of Life one, which he co-founded from the very beginning, but he's on every one because everybody wants him. He invents new ways to look at stuff. And there are very few people who actually can do that, know how the atoms and the light works, and also being able to actually go into the lab and make it work, make it do something, not just the laser craze, laser tagging game. So, but it's fun too. So I hope you enjoy both the beautiful imaging that you will see, the images, and also the depth of the physics, astrophysics, and science that you're going to hear tonight. So without much ado, let's let Ron do the rest.
Thank you. Thank you, Dimitar. So welcome. We're going to have some fun tonight. First you're going to have this talk, and then we'll have the fun afterwards with the observing and things like that. So yes, I'm Ron Walsworth. I'm at the Harvard Smithsonian Center for Astrophysics. We'll get to what this beautiful picture is later in the talk. I really have one message, and I'll back up with two stories. There's really three stories, but we won't have time to get to the third one. I'll just mention it briefly at the end. And that one message, and this is related to how I can measure things and invent ways to do lots of different types of experiments, is that everything is quantum. Everything that we know of in the universe can be described by the laws of quantum physics. And those laws are actually pretty simple. They're pretty cool, pretty profound, pretty simple. And so when we want to measure things or image things, we do things using this cutting edge ideas that come from quantum physics. And then when we develop a tool to be able to image or measure something, it might be an atomic clock, a way to measure magnetic fields, a way to image deep inside the body or stars far away, those tools can find applications very broadly, not just in the problem you're trying to solve, but more broadly. So everything is quantum. Atoms certainly can be described by quantum physics. Dogs, cats too, even people. And of course astronomical objects, galaxies, etc. When we look at stars far away or galaxies far across the universe, we look at the hydrogen atoms or the helium atoms and the light that they emit, it's very much the same as the atoms we study in our laboratories. The laws of quantum physics apply across the universe, and that gives us a lever arm to be able to invent and learn about the universe. So what are those laws of quantum physics? Well, you can take courses on it, and I'm just going to summarize pretty quickly. There's a few. The fundamental properties of nature are quantized, meaning they come in discrete units, discretized. Things like energy, momentum, charge, the wavelengths of light that atoms emit, etc. There's something called wave-particle duality. Everything can be described both by its wave properties and that it's a particle at the same time. That's some of this funny stuff that makes it a little bit hard to understand, but that opens up a lot of opportunities to make better measurement tools. And there's the uncertainty principle, which puts limits on how precisely we can measure things. So if you account for these sorts of laws, you can make better tools. And early in the 20th century, pioneers like Schrödinger and Heisenberg and Bohr and many others laid down these laws for us. And that history is really interesting, but that's not today's talk. Today's talk is how to take quantum physics and explain nature and develop new tools, new capabilities to help life on Earth as well. So what's one example? You know the global positioning system that your phone uses to tell you where you are and where you're going, or that helps navigate planes and all sorts of things around the world? That's based upon a series of atomic clocks that are on satellites. That's a quantum tool. Those atomic clocks and the signals they emit depend upon the laws of quantum mechanics. Without them, it wouldn't work. If each atom was different from each other, or they could emit any old signal, we wouldn't be able to have the properties of atomic clocks which allow us to navigate and communicate. So let's say there's 3 satellites, you're sitting at some location. The signals sent from the atomic clocks to your detector take some time to arrive. That time is set by the speed of light, the finite speed of light that we know. But the ticking rate and the time kept by the clocks is so similar one to the next that the longer path and the shorter paths, the differential arrival time can tell us where you are. And as you move, the Doppler shifts in the frequency of the signal sent by the clock can tell you how you're moving. So it all depends upon quantum physics. So what we do in laboratories around the world, mine downstairs as well as many others, is we build tools based upon quantum physics. And we build bridges to people who might use those tools. So it's not just us coming from one side of the river, bringing our quantum tools from the lab. It's also talking to people like the astronomers who might want better tools because they're interested in questions in cosmology or exoplanet science. They want to figure out and find Earth-like planets around other stars, for example. And so building tools can help us understand nature. It also can help life on Earth. Each of these examples here I'll get to and what they are and how they're beginning to help life on Earth. So that's a teaser for later in the talk, okay? Remember those nice little pictures. Okay, I got 3 stories. We're really going to do 2, and then quickly one at the end. Story number 1, which is a blast from the past, blast from my past. It's 1991 to 2008. What was going on during that period down in the laboratory downstairs? we were building a special type of atomic clock. Not the atomic clock that was going to go in the satellites and help the global positioning system. It's something we called the dual noble gas maser. So this is a story about building clocks and what they were used for. And we were trying to answer this question here. Is there a preferred direction to the universe? If you're far out in deep space, you know nothing, are the laws of physics the same no matter which way you point? Or is there actually a kind of directionality to the universe, so that the masses of particles, electrons, neutrons, and atoms, the speed of light might change slightly depending upon whether you're in this direction or that direction? All evidence to date said no, it can't be a big effect. But there were theoretical motivations at that time coming from string theory and ideas like that that said maybe there is a small effect. And the best tools we knew to answer such questions were clocks. And so we built a particular type of clock to try to address that question specifically. This clock used two types of atoms, helium-3 and xenon-129, all mixed together inside of the clock. Helium-3 and xenon-129 are quite different and quite similar. They're both noble gases, chemically inert. They both have a nuclear spin that creates a quantized nuclear spin that can point in the up or the down direction that is the source of the magnetic signal for the clock. But they're very different in their masses. Helium-3 just has 2 protons, 1 neutron, and 2 electrons, whereas xenon-129, 54 electrons, 54 protons, and 75 neutrons. So very different masses. So if the masses of the particles change with the directionality of the universe, they would distinguish between that. But otherwise, they're very much the same, and the quantized spin that they have, which is like a little magnet inside of them, is very much the same. So, see here? Now the arrow points down. So this is really the thing. The spins can point either up or down. Up or down. I do this a few more times, people get bored. Okay, up or down. Because the differences in the masses, the atomic clock signals, these radio frequency signals that the helium-3 and xenon-129 give off, are at different frequencies. And those are the signals we were monitoring in this one atomic clock and asking the question, do those signals change with time as the Earth rotates and moves around the sun, as it reorients the laboratory compared to this directionality in the universe that may or may not exist? So there was our lab in 2003 downstairs. Lab's still there. The experiment doesn't exist anymore. It kind of looks like a lab experiment, doesn't it? A whole bunch of stuff, metal can, boxes of lights on it, wires all over the place, held in a wooden container, so this is like built from scratch by grad students. Guys like this. Well, there's me in the corner, but the students and the postdocs who were working on that at that time. Nat and David and Federico and me. Okay, at that time. So we worked hard for many years, and we monitored the signal of our clock as the Earth rotated and went around the sun. And we were just building up data. Is there any tiny effect that we could see as we monitored these signals from helium-3 and xenon-129 as this clock operated? It took a lot of years to get the clocks working well, of course, then many years of monitoring the signals. So after these many years and this wonderful clock working, we got an answer, at least as well as our clocks at work, which were the best in the world at that time. And what do you think the answer was? Is there a preferred direction in the universe? What do you think?
Yes.
What do you think? No? Yes? How many think no? Hands up for no? Okay, everyone else says yes. You can also say, I don't know. This talk is boring. I want to go observing. Okay. The answer was no. How well did we know no? Can you know anything perfectly? Science has uncertainties associated with it. How well could we tell that things like the masses of atoms are not changing as you reorient them in space to 1 part in 10 to the 31? Yeah, we were persistent. I guess we didn't have a lot other to do, but we kept going. Actually, we stopped after about 2008. And others, and believe it or not, with other devices, have kept going. They've added a couple more zeros. Still no preferred direction of the universe. Okay, maybe it isn't there. The effects are supposed to be tiny, but we worked hard. For that big zero that we found, or something close to zero, I actually won an award. Look at me. That's me back in 2003 or 4. Look, nice young me. Look at that smiling face. I won this award, the Francis M. Pitkin Award. Who was Francis Pitkin? Frank Pitkin. He was a professor in physics department at Harvard. Actually, he was when I was in grad school there in the 80s. He was on my thesis committee. Wonderful man. By this point, unfortunately, he'd passed away. And because his expertise was in precision measurements, some people had made it there'd be a prize in his honor. So he was a wonderful man. I want to remember him. But I put something in red box here because I'm going to transition from this experiment into its helping life back on Earth. It said I also won this award for applications of masers. I was talking masers to imaging. Okay, what was that? That wasn't anything I was telling you. And what they meant was biomedical imaging. In the 90s, I'd realized that because noble gases are inert, save for humans, and they can be, and others had realized this too, it can be easily imaged with magnetic resonance imaging, MRI. These are chemically inert. They don't dissolve and do nasty things inside your body. So maybe it would be a useful tool to make a simple, low-cost, portable MRI machine. Low-cost portable MRI. That was the goal. In parallel with us building these clocks and doing these things, this, in parallel, was what we were doing. We had our first prototype things that weren't ready for humans. There's the wood box again, and more wires and copper and funny-looking electronics and all that stuff. We were taking images of gases inside of glass chambers that had funny shapes. When I would show this at conferences in those days, they'd think H meant Harvard, but I say, no, it meant helium for helium-3. Come on. But by 2005, we built our own walk-in MRI machine that was operating downstairs in the basement here. And we'd get people like myself would stand inside of it. You could stand, you could sit, you could lie down. You did not have to go inside a tight tube. How many people have had an MRI? Remember the tight tube? Remember how claustrophobic it is? Oh, you can't go in there because the magnetic fields are really high. Remember, it's kind of scary? Remember that all the funny noises? This doesn't have any of those things. It's open. It's cheap to build. No funny noises. No claustrophobia. Operates at low magnetic field. And in the early days, we were things like inhaling helium-3 gas. We could image for the first time where the gas goes in the human lungs. By 2014, we had a next-gen system and got offered a laboratory over at Mass General Hospital and moved it there. We'd figured out ways to not need the noble gases, and we were starting to do brain imaging that was approaching the capabilities of the high-field, not portable, super expensive devices. So at that point, time to commercialize this. This is looking good. We need to think about a way to engineer them up so they can really get out and help people. And that's what happened. So now, by 2018, there are portable, low-cost MRI machines which can roll around on wheels, rotate around, come to the patient. Now, you don't have to schedule and sit in the waiting room. This comes to the patient. It goes up around the patient, maybe in a bed, in a hospital bed. Maybe we can have it on in ambulances and doctors' offices, things like this. Its cost is targeted to be about 1% of the cost of traditional MRI. It's currently in 3 hospitals for testing, hopefully for sale in about 2 years. Here are the scientific advisors for this company. They include people like David Ferrucci, who led the team that developed IBM Watson. Max Tegmark, a famous cosmologist. There's that same picture of me again. Okay? And I must declare, since I'm a co-founder of this company, I have a financial interest in it, which is important to let people know. Right? So there's a bit of an advertisement here going on. But the man who's most important in terms of actually going from not at the technical stage but making it work as a company is this man, Jonathan Rothberg, who in 2016 received the National Medal of Technology and Innovation from President Obama. Remember him? For his work in his previous companies, driving down the cost of human gene sequencing. He's the man primarily responsible, through his companies and his inventions, of taking human gene sequencing from a multi-million-dollar per sequence down to thousands of dollars, that sort of thing. And now what he's trying to do with this, and some other companies he started, is drive down the cost and increase the performance of biomedical imaging so we don't always have these giant, expensive things stuck in hospitals. All right? I also want to thank something very important. The early days back in the mid-90s when we first had this idea, and it was very crude, and we were trying to build the atomic clocks and find out whether there was a preferred direction of the universe, there was the initial seed funding we got came from the Smithsonian Institution through the George Birch Fellowship. There's George Birch, Dr. Birch, deceased now. But the Smithsonian put in, I forget how much it was, Sarah, do you remember? 50,000, 100, some number like that. But it was key, otherwise we couldn't have begun. We couldn't have built the thing on the wood box and done those things with the H's. We couldn't have done the early tests that led later to what you see. So going from these sort of ideas and testing these things to a portable MRI machine that can do this starts with, yes, the scientists and the idea, but somebody has to believe in it enough to fund the first stages. Okay? So that's story number one. You like that story? Excuse me. So now story number two. Diamonds. Something very different. Diamonds. They look beautiful, don't they? Turns out diamonds often have defects. They're not always perfect. The carbon lattice is not always perfect. And the defects can give them colors. Real colors. Perhaps you've seen colored diamonds before. That image that I showed at the beginning is actually diamonds. Not the diamonds cut into gems, but tiny little diamonds that are, like close to a millionth of a meter in size. Tiny little microscopic diamonds that end up having defects, not because we placed them in there, but sort of naturally. This is diamond's grit that is used for grinding. And the defects, different colors, are different types of defects. The defects can often have, quantum properties that we can take advantage of. So here's a cartoon of the diamond carbon lattice, where each of these here blue balls are the carbon atoms. And inside a diamond like that, if it's pink, 2 of the neighboring carbon atoms are replaced by a nitrogen atom, N, and a missing carbon atom, a vacancy as it's called. And this is called an NV, nitrogen vacancy, color center. And then you have lots of them. Over here in the carbon lattice is another one, and over there's another one. If you have enough of them, they make the diamond be pink. All right? It's been known that these NVs exist, and there are lots of other defects too for many years. But starting, I'm getting ahead of myself. Let me tell you some more properties of the NVs. They have quantum properties. Let me go through what the quantum properties are. 1, they emit 1 photon at a time. If you illuminate room light or green light, they'll send out energy in 1 red photon, 1 at a time. So they don't emit them in bunches. They get energized in 1 at a time. They also, again, have spin, like those helium-3 and xenon-129 nuclei did, but not the nucleus now. It's an electron spin. So it's much more sensitive to magnetic fields than the helium-3 and xenon-129. And that spin can point in one direction or in the opposite direction, just like we were talking about with the helium-3 and the xenon-129. Really, you can think of this spin as being like an atomic scale magnet. If it's pointing in this direction, north pole of the magnet in this way. If it turns around, north pole that way. Okay? It both emits magnetic fields due to its orientation, and it's sensitive to magnetic fields. And if you have the NV and the spin oriented in this direction, it will emit photons at a fast rate. But if you turn it around the other direction, the photons come out more slowly. Okay, that's just a fact of nature that we can understand with quantum mechanics. It's interesting, but it also gives us a way to determine which direction the spin is pointing. Is it a fast rate of photons or a slow rate? And that gives us information about how the magnet is oriented. So what? So that's okay, but so what? Here's actually an example of a diamond in a laboratory doing measurements, glowing red under green laser illumination. In the period from the late 90s to about 2006, some scientists, because of these quantum properties, were thinking diamond might be a good host material to make a quantum computer. Interesting idea, but there was a problem. This annoying need to control the magnetic fields because, let's say you have a magnetic field in this direction, the magnet wants to line up, but let's say it turns around due to some fluctuation, and now your spin has reoriented itself, and that can mess up the operation of the quantum computer, because the quantum computer is trying to do calculations essentially based upon these quantized spin directions. So that was an annoyance, and people were spending time trying to figure out ways to deal with these technical challenges to make their quantum computer systems work well. In particular, a colleague of mine in the Harvard Physics Department named Mikhail Lukin was busily doing this sort of thing, and he was busily wondering about these technical challenges and how to solve them. Another colleague who came from Berkeley visited, heard about these things, and said, well, if it's so sensitive to magnetic fields, maybe these defects inside a diamond would be good sensors of magnetic fields. They could be good magnetometers. And Misha said, let's ask Ron. We work together because I'm the guy who thinks about how to measure things very well. And as soon as he told it to me, I went away and thought about it, did some calculations, thought about what you could do with it, and I realized, it could be a very useful magnetometer. So, by 2007, we'd taken several of our students and postdocs from several of the research groups, shown in this picture, together. This fellow wasn't there that day. Got them together and started developing demonstrations about whether these quantum diamond magnetometers could be any good and could be useful. By 2008, we'd shown they could be very useful and published 2 key papers that appeared in the journal Nature showing this. By 2010, DARPA, the funding agency, had taken notice and started a whole program on quantum-assisted sensing and readout based upon this kind of technology. So the government really, through this program and others, started pumping a lot of money, your tax money, thank you very much, into funding those young students you saw on the other page for them to do a lot of the hard work and buy the equipment and whatnot. Over the following decade, the number of scientific papers published per year grew as people around the world began using this technology for lots of different basic science applications. Okay, that's nice. So what? Basic science applications by people in the lab with funny diamonds. What are some examples of how you can do anything useful with it, learning about nature, and maybe helping life on Earth? So I'm going to give you 2 example applications. 1, origin of the solar system and origin of life on Earth. It's believed, it has been believed for a long time, that magnetic fields played a key role in shaping the formation of the solar system. As the gas dust cloud that preceded our solar system underwent a gravitational instability, most of the mass ended up in the proto-sun, and there was a swirling plasma dust disk around it, from which, we believe, planets formed over time, over a few million years. Instabilities in that plasma dust disk, driven by magnetic fields from the electrical currents in the plasma, as well as from the sun, etc., are thought to have played a role in helping to determine where the early planets were being formed, and at least the bits and pieces that led to the planets. Okay, is that story true? Is it just made up? What were those fields? Do we have any evidence of what the magnetic fields were, and are they consistent with its ideas that they're big enough, as a function of distance from the proto-sun, to play a role in that way? Well, do we have a time machine to go back 4.5 billion years and study them there? No, we don't have a direct time machine, but we have a kind of time machine I'm going to tell you about. Also, the magnetic fields from the early Earth, as the Earth was forming and after it formed in those first few 100 million years, are thought to have been key as the geodynamo got going to shield the Earth from charged particles from outer space and allow life to get started. When did the geodynamo begin? What were the magnetic fields in the early Earth? Do we have a time machine to go back and explore that? No. But we do have ancient rocks and meteorites. There are rocks that exist on the Earth that are more than 4 billion years old. Here's Professor Roger Fu from Harvard in Western Australia digging some of those up. There are also occasionally meteorites which fall to the Earth, the insides of which the chemical composition and isotopic ratios indicate are bits and pieces left over from before the planets formed. And maybe these ancient rocks and these meteorites can carry signatures in iron-bearing grains that are very special of what the magnetic fields were when they formed, and we could learn about what these magnetic fields were as the planets were forming and in the early Earth. We've been doing that with a device we call this quantum diamond microscope, based upon these NV centers in diamond and being able to image magnetic fields. Here's an example of one sitting right downstairs in the lab. It's about this big. We're building them now for many labs around the world. So, for example, the Allende meteorite, it fell in Mexico in 1969. The outer surface gets very hot. Inside, though, was a cool component that later fell in the hands of scientists. They cut it up, looked at the slices inside, identified some of the key regions that were these old components inside, and wanted to know what are the magnetic fields associated with these regions, these tiny kind of little small regions. Look at the length scale. This is a millimeter here. And the really interesting part is right at the boundary. So if you zoom in with a regular microscope, you can see the rock, but you don't know what the magnetic fields are. You put it on the quantum diamond microscope, and yes, you can. Okay? So it turns out from measurements like this that we now know that the ancient magnetic fields that existed while the solar system were forming are about 100,000 times larger than what you see in interplanetary space today. And that means these ideas, these magnetic shockwave ideas in the early plasma dust cloud were probably related to inducing planet formation. Similar things about the geodynamo of the Earth are still being studied. The same technology we've redeployed also for single biological cell medical diagnostics because magnetic fields pass through tissue. The way MRI machines work, remember we talked about MRI machines before, involve magnetic fields coming from the nuclear spins inside your body. The reason you can image so well inside the body with magnetic fields is they pass through largely undisturbed. The same thing magnetic fields could pass through, let's say, in a blood sample, if you want to do a diagnostic. Let's say there's a bad cell that exists, or you want to know, are there any bad tumor cells in my blood sample? You want that answer accurate. If there are bad cells, you want to know. If there aren't bad cells, you don't want a false positive. You want an accurate result. Our idea is label the tumor cells reliably with magnetic beads, because magnetic fields pass through tissue. So if I take one of those cells and plop it into a sample of blood, there's a lot of blood cells here, and I do an optical image of all the blood, and I ask the question, where's the tumor cell? You cannot tell. Do you know where the tumor cell is here? Does anyone know? Can you guess? You can't tell, because it's nothing special about it in terms of optical images, and the thick, soupy blood there absorbs a lot of the light that you try to use to image it. However, as I've said several times, magnetic fields pass through tissue. So if you take the same sample and place it on the quantum diamond microscope, voila, you can see that's where the cell was. All right? Okay, that's a nice demo. Does it work at scale? Oh, yes, it does. You can do many cells over large fields of view. Every time you see a blue-red thing here, it's another one of these labeled cells. And you can do it with very low false positives, very reliably. So again, this meant we maybe have a technology that we can use to find bad cells and save lives. And so there is a startup company, I'm a co-founder of that one too, in which it's trying to take this technology and commercialize it for these purposes. The goals are 100 times more sensitive at finding these bad cells, 10 times faster than any existing technology. Minimal waste products, again, the other alternative technologies are huge instruments that involve a lot of waste chemicals. This technology is not. Much smaller device, much lower cost. We've already built one of these small, or several of these small boxes. They're now working with partner companies that might be users of this sort of technology, not available for sale yet, but undergoing testing. The company's called QDTI, Quantum Diamond Technology Incorporated. And again, I'm an advisor and have a financial interest, so I want people to understand. Okay, that's the diamond story. Remember these folks? They were students and postdocs back in 2007. Where are they today? What are they doing? All over the world, many professors, some in industry. Jake Taylor here is actually the White House science advisor for quantum technology. I don't know if you know it, that there's likely going to be a big national quantum initiative announced. There's bills going through Congress, bipartisanly supported, believe it or not. The White House is actually supporting this sort of thing, and Jake Taylor there, who was a grad student at Harvard, he was actually an undergrad at Harvard and did astrophysics in his early days, if I remember right, is the White House science advisor. Okay, story 3, don't have time. Well, I'll just use one slide quickly. There's a device called the laser frequency comb, which was invented by the two men on the right here, and they won the Nobel Prize in 2005 for it. By 2008, we'd realized we could adapt that laser frequency comb to serve astrophysics. We built, by 2014, we had an operational system that was sitting in the Canary Islands. Why the Canary Islands? That's out there in the, off of the coast of Africa. Because in the Canary Islands, there's a nice telescope and spectrograph, and we can use it to improve the spectroscopic performance of that telescope. That's going on today in a way that can help find Earth-like exoplanets. That's work I do together with Dimitar and many other key people. And because one of the ways that you find exoplanets is by seeing tiny Doppler shifts in the light that comes from the star as the planet goes around the star. Tugs on the star, the planet does, and you get a blue shift and a red shift back and forth. That as the planets get smaller and smaller, those spectroscopic shifts get tinier and tinier, and they get harder to see, and you need quantum technology to be able to make the instruments good enough to see things, and they have to be stable. So these astrocombs are locked to atomic clocks again. They keep coming up so that you have very stable performance over years. Because I bet you know how long it takes the Earth to go around the sun. And if it's an Earth-like planet around a sun-like star, it's going to take a similar time. And you want to see several orbits before you're confident. So it's going to take stability over years. Only atomic clocks can provide that. That same technology has been developed into field operable systems, which are now being used for real-time monitoring of trace gases, like greenhouse gases and pollutants, over large areas at sensitivities much below any other technology in real time. I'm not involved in that activity. That's other scientists who are doing that sort of thing. I want to be clear about that. But it's the same core technology, again, that's being able to help us explore the universe and help life on Earth. Okay. I'm coming to the end. Didn't even take all my time, did I? Yeah, okay. So my message is everything is quantum. We have to understand quantum physics if we want to do things at the frontier in terms of measuring and imaging. And with quantum tools, we can build bridges to lots of different fields and help life on Earth. Thank you. I'm here to answer, happy to answer questions. I will start by one question that people often ask. Aren't diamonds expensive? Answer. Did any of you ever wondered why diamond rings, like engagement rings and this sort of thing, Sir Joy, if somebody scrimps and saves, they can just barely afford it, and basically all their money goes just barely afford it? Does anybody think that happens? Is that an accident? Or do you think perhaps a cartel is maintaining the price at a level to extract the maximum amount of money out of you?
Answer B.
Yes, exactly. So diamond gems are, to some degree, artificially kept expensive. The kind of laboratory-grade diamonds, which in many ways are superior to diamond gems, that we use for a lot of these sensing applications. The research is expensive, you've got to pay people, but once they're ready, those things are much less expensive. So these QDTI boxes or the quantum diamond microscopes we're using for a lot of the scientific applications, it's the diamond itself is not the key expensive one.
Okay, questions? Yes.
I've always found it fascinating that the tug of the mutual gravitational interaction between a small planet and a star is such that you can actually detect the star's change. What is the limit of threshold for that motion?
So humans can't yet detect something as small as an Earth around a sun at the Earth-Sun distance of 1 astronomical unit. The tug there, I can tell you what the numbers are if you want to know. It's about 100 kilohertz in frequency, the shift, right? Which is large in a laboratory sense, but is actually about a part in 10 to the 8 of the shift of the width of the spectral lines you're using from the star to see. So humans can't yet see that. That's what we're trying to do with these technologies. If you go make the planet a little bigger, the star a little less massive, or the planet closer in to the star, then the effect of gravity on the star is the planet's gravity, is larger, and the star moves more, and so these big blue shifts and red shifts get larger, and the spectral lines shift more, and humans can use that technique. And in fact, those were the techniques, these radial velocity or Doppler shift technique or wobble technique, it goes by all those names. That was the technique that in the early days of exoplanet discovery, the 90s, early 2000s, was the dominant technique that was being used to discover or target exoplanets. The other technique that many of you have probably heard of, there's a star, and things are lined up and you're the telescope, and the planet passes in front of it periodically, you will get a small decrease in the amount of light that comes from the star. And this transit photometry, measuring the light from the star, and then boop, 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 every time the planet passes in front, that is also become a leading technique. And space-based telescopes like Kepler that do a lot of the discoveries these days use that technique primarily. Ideally, you'd like to have both. Let's say for multiple reasons. That is, you'd like to use both techniques, the radial velocity technique and the transit photometry technique, and one, to see that they agree. Right? And when the planet is supposedly passing in front of the star, it should be also causing a tug that you should be able to detect the blue shift and red shift. If they're inconsistent with each other, then maybe you're not seeing a planet, maybe you're seeing a sunspot or something else is going on. Right? But also, they, in addition to confirmation, they provide complementary information. The transit technique, they both tell you about what the orbital period is, how long it takes. Okay? Right? The transit technique gives you information on the planet diameter and hence volume, because you know typically how big the star is, and so you can see how big the shadow is that goes across, and that's planet diameter or volume. The radial velocity technique, since it's force of gravity, tells you something about the planet's mass. Different things. And if you know the mass of the planet and the volume of the planet, because you've used both techniques, mass divided by volume is mass density. And knowing the mass density is very important, because then you can say, the average mass density of the planet. This is an ocean planet. It seems to have the density mostly of water. This is a gas giant planet. It seems to have the density close to hydrogen or helium, mass density. This is a rocky planet, a rocky metal planet, kind of like the Earth. That would let us characterize the classes of planets. It's not the end of the story. We want to know much more about these planets. Ultimately, of course, we humans, once we've got good target candidates, we'd like to isolate the light that comes directly from the planet not just the light from the star, and do spectroscopy of the light from the planet, as well as ultimately image. Take, this, like those nice cartoons I was showing, wherever it was. Let's go back. Story 3, sorry. This, like, that's a cartoon, obviously. We don't have beautiful pictures of Kepler 186f, right? And you see lovely artistic renditions and imaginations of what the planets look like. We don't yet have the ability to do spectroscopy or imaging, really, of planets, exoplanets. That's a dream for the future, but a dream that people are dreaming and thinking about the technology would be. So I'll ask the audience here, what do you think is the hardest thing? What is one of the number one challenge, technical challenge, in directly detecting the light from a planet? Something, yes?
The main challenge for directly detecting the light from the planet is that the star's light can block it out. Also, it's so far away that it's very dim, and you can't really see it very well.
Wonderful answer. You're largely correct. The first part was really correct. If you take stars and planets that are really close by, I do this in my physics classes at Harvard sometimes, and I will do a calculation. How many photons from a typical planet, from an Earth-sized planet, let's say, and a sun-like star, put it like 10 light years away, not too far away, and just think about the reflected light coming off the planet to the Earth, and then take a big telescope and calculate how many photons would be coming in, and compare it to the number of photons that are coming in from some cosmologically distant source, billions of light years away, that we know we can detect from some distant galaxy. Turns out often the planet photon flux is larger than this cosmologically distant source. So it's not that it's dimmer in an overall sense, but it's what you said, exactly what you said at the beginning. It's a dim, not super dim, let's call it dim thing, really close to a super bright thing, right? The star that you're looking at. And the separation, obviously, it's not super close, it's like millions of miles away or something, yeah. There, it's millions of miles away, but we're light years away, and so the angular separation is so tiny that our telescopes don't have the ability to distinguish that bright light source, the star, from the dim one, the light off the planet. If you calculate how big the telescope would need to be, it's unreasonably large to separate them. So people are thinking about clever ways, interferometric ways, to screen out the light from the bright light from the star so you can see the light from the planet. Good answer. Are you a student at Harvard? Yeah.
No, I'm only in high school.
Oh, okay.
Okay, wait, they're supposed to ask the questions, not you.
I'm turning into the
There, we have a question. Yes,
Yeah.
please.
So I wanted to ask about something sort of small, but the portable MRI machine
Yeah.
that you mentioned in story 1,
Yeah.
the image didn't have any comparison to an object, any other object. Like, how large is it? Is it like, the kind of size you put your arm into, or the kind of size that you lay on?
It's a great question. You're right, I didn't have that. So it's about this high. It's got a base like this. You saw it had wheels that could back up, and it has this magnet thing that rotates, and it can pivot and come up around. So it's like a cart, kind of heavy cart. You push it around like this, and you can come up and image somebody, right? So it's not a tiny little handheld thing. Maybe in the future we'll get to handheld MRIs. But it's taking, I don't know if you've seen a conventional MRI machine is like a big old giant thing that can't move, and now we're gone to a cart that can move up to the patient in the emergency room or wherever. That's how big it is. Great question.
A question from you.
So you said that diamonds are being put into the designs for quantum computers. Are there any other materials that are also being looked at? And if so, what is the difference between those and the diamonds?
Awesome question. So yes, people are still thinking some about diamonds for quantum computers, but they're not currently the leading technology for quantum computers because of a lot of the problems, in addition to the magnetic field problem I mentioned, which we turned into an advantage for sensors, okay, and imaging. Also, if you really wanted to have a great quantum computer, you couldn't have just one of those NVs and then another one over here, another one randomly. You'd want to be making them in an array, so they'd interact with each other in a very uniform way. So the struggle in that community now is to be able to make these defects not just an average density and somewhat randomly arrayed, but very uniformly arrayed. That's a major challenge. So other technologies are currently at the frontier. The two primary technologies which are the leading modalities for quantum computing today, which may not be forever, are things called superconducting qubits, superconducting circuits, which operate at cryogenic temperatures, and their quantum property is that they only allow specific amounts of magnetic flux through them due to the quantum interference that occurs in the ring of superconducting metal. Superconductor means it does not have any resistance. Okay, that's one. And the others are arrays of ions in an ion trap. So atomic ions, all exactly the same. And in that case, the interactions between the ions, static interactions, are so strong and so uniform that when you put multiple ions, they repel each other. But then they're stuck all repelling on each other. They form a natural array or a chain. And you can do quantum computing up to a certain point with either modality. There are other materials people are looking at based upon silicon and other things, but those are the two leaders right now, and almost all of the companies that are commercializing quantum computing still in the early days are using one of those two.
So we have a question there and there, but we'll be finishing soon, so just very briefly.
Okay. How did you mark the tumor cells again? Like, it seemed like there were 1,000 that were marked, and I'm like, how is that done?
Right. So the tumor cells are marked with magnetic nanoparticles, which themselves are chemically covered with a ligand, which is targeted to attach only to the known the known biomarkers on the surface of the tumor cells. Right. Then you might say, okay, great, maybe that works, and maybe in the example I showed of a lot of cells, that was an example in which many tumor cells were purposefully put into a blood sample just to demonstrate, look, we can see so many in parallel, right? A thing you might worry about, and has been worried about, is, okay, maybe they can label these cells with magnetic fields, and the magnetic fields pass through tissue, and they go into the diamond, you can see them. But what about all the other magnetic nanoparticles when you're doing your mixing? There's going to be some left over, and they're going to give you false signals, and now you're finding a bunch of things that aren't tumor cells. So yes, that's an important thing. That problem's been solved by the fact that the way the magnetic nanoparticles work is that only when they're labeled do they give off a distinct signature. On their own, they don't. I can't tell you why, because that's a patent-controlled secret inside the company. But that was a key thing, and there's lots of other things the company has to control. But so they have their magic sauce. It's sort of like the ketchup recipe or something.
Okay, so last question there, and unfortunately we have to.
Okay.
Oh yeah.
I think you mentioned that when you're looking for other planets that might be Earth-like,
Yep.
that you're looking for like a 365 day rotation. Is that
Period.
one of the?
Yeah, we're going to go around. Now, if it was the Earth is 365 days approximately,
Right.
But if there's some other planet that's close to the Earth's size and the Sun is not exactly like the Sun, and maybe it's 314 days, it's not 365 necessarily.
Okay.
That's our Earth and our Sun. That's just
Gotcha.
a typical value.
My question was just like, is that a requirement to be Earth-like?
No.
Okay.
No, it's not like if you're 364 days. Sorry. No, it's we, to be honest, Tim Char's an expert in these sorts of things. I am not. But I think the scientific community really doesn't know yet what are the requirements to be sufficiently Earth-like to, let's say, have life or something like that. We can calculate things like what would the average temperature on the surface of a planet be, given how far away from a star it is. But even that, we're not sure, because maybe the weather or something like this changes things. There's greenhouse effect or not. So these are very rough terms. So there's a thing called the habitable zone that astronomers talk about. On a given star, a distance away, there's a region, inner radius, outer radius, which we calculate is approximately the region in which liquid water on the surface of the planet would exist. But that's a rough calculation, and until we know more, we can't be very sure about these things.
So if you have more questions, and I'm sure some of you do, please come now and talk to our speaker. But in the meantime, let's thank him again for a marvelous lecture.